So we will use this example right through this session to explain the maximum flow problem. So what is the maximum flow problem? Given a network which has nodes and arcs, in this case directed network, it also has arc weights. It has all of them. Pi node, I guess 3, 4, 5, 6, 7, 8 arcs. We want to find out maximum flow on this network. One way of looking at it is, 1 is called the source, 5 is called the sink or destination. Usually in maximum flow problems, you use the term sink rather than destination. So something is flowing from the source to the sink. An infinite amount of that something, which is water, fluid, oil, traffic, money, goods. One type of commodity is flowing. How much can I send? Obviously, I can send only in the direction of movement. That's why it's a directed graph. The weight actually represents something like a capacity of every arc. If you can imagine like a water distribution system, and each of this arc is like a pipe, which can do certain amount of discharge. So 1 to 2, I can send only a maximum of 20, and so on. What is the maximum flow possible in this network? It's a very simple problem. Sometimes you can have bidirections, you can do many things. Usually it is assumed, and it is true, that the arc capacities are all non-negative. You don't have negative arc capacity. Customary to use integers. You can modify it for fractions and decimals. Algorithms even exist for irrational numbers as capacity and so on. Root 2 and all that, they do exist. But today we are not going to see with irrational numbers as arc weights. We will look at integers. If you have any fraction or decimal, you can conveniently multiply it to get an integer. So we will restrict ourselves to integers. And because only one commodity is flowing, we will have only one arc from given any two nodes. I don't have a 1 to 2 and a 2 to 1, because the same commodity is flowing 1 to 2 and 2 to 1. If 1 to 2 capacity is 20 and 2 to 1 capacity is 10, I can replace it with the net direction 1 to 2 as 10. All right. So there is only one arc between two given nodes. Direction doesn't matter given in the network. Right now I have chosen a very simple network to explain. I have not complicated the network. The purpose is to understand the algorithm. Our capacities are given. The easiest thing to do for me, for an OR person, is to solve it as an OR problem. Not look at it as a CS way of looking at algorithms. But that's not what I have come here for. So we will do the algorithms as well. But how do I solve it as an OR problem? So I solve it as an OR problem by saying let xij be the flow in arc ij. So let x12 is the flow in arc 1 to 2, x23 is the flow in arc 2 to 3, and so on. So there are 8 arcs and there are 8 variables. Each arc represents a variable. This is a flow. Let f be the maximum flow or flow in the network. So obviously I want to do the maximum flow, so maximize f. Variables are 8 variables that are given here, x12, x13, x23, and so on. So I formulate a linear programming problem, so maximize f. F is the flow that I wish to maximize f. Now obviously the flow has to start from the source, and therefore f is equal to x12 plus x13. Whatever flows in this plus whatever flows in this is the total flow. That's my first constraint. What is my second constraint? If I take this, I don't have any way to retain any flow in a node. Flows at the end of the day happen between the source and the sink, and all intermediate nodes don't have capacity to retain flow. Therefore, the net flow has to be 0 for all intermediate nodes. So if I take node 2, what comes in is minus x12, x25 plus x24 plus x23 is equal to 0. What comes in has to go out. Either I can say x12 is equal to x23 plus x24 plus x25, or I can say minus x12 plus equal to 0. Similarly, I can write for the third and fourth. Finally, whatever reaches, the flow F has to reach the sink. So F is equal to x25 plus x35 plus x45. For reasons of convenience, x25 plus x35 plus x45 equal to F. Actually speaking, at some point I will multiply this with minus 1, but it does not matter. It is an equation, so I am okay. Xij greater than or equal to 0, F greater than or equal to 0. Okay? That is an easy way to formulate this problem. And for such a small and simple problem, what I do is I do this formulation. I go, and of course, I should have the capacity. Otherwise, I can get infinite flow. So I have the capacities which restrict. So Xij less than or equal to Uij. So x12 less than or equal to 20, x13 less than or equal to 40, and so on. So a general problem with n nodes and m arcs. So you have as many variables as the number of arcs, and as many constraints as the number of arcs plus number of nodes plus 1, the way I have written that F is coming. Right? So given a network with n nodes and m arcs, I have n plus 1 variable and m plus n constraints. All right? I know that I can make this slightly better by eliminating this F, because F is anyway an equation that comes here. So I can substitute for F is equal to this. I can knock off one of the constraints, so the problem will reduce to this, even something smaller than this. Because all of them are equations, I can just play around with equations. I can eliminate variables, so I will get this. So you see, I have one variable less, F is not here, and I have two constraints less. I can do that. And I just go to the Microsoft Excel solver, which can solve linear programming problems. Okay, so you don't have to break your head understanding the matrix method and eta factorization and all that. That is when you ask a question, what goes inside. If you want to solve LPs, just quickly get a free downloadable solver somewhere from some common available resource, or if you have a copy of Microsoft Excel with you, Microsoft Excel can solve linear programming problems. So put it into the Excel solver to get this answer. So 55 is the maximum flow that is possible. You have multiple optimum solutions, but it's okay. 55 is the golden number for the next 1 hour. Okay, 55 units of flow. So I have already given you the answer, there is no suspense. But how we get this 55 in so many ways is what we are going to see in the next 1 hour. All right, fine. So this part is over. This part is a continuation of the first part. So we understood simplex. You can put it in simplex and solve it. You will get this answer. Right. How else can we solve this problem? But we also know that simplex is what? Simplex is not a polynomially bounded algorithm. So for very large networks, the running time may be very high. So can I design and look at more efficient algorithms that can actually solve it faster and better, which is the curiosity of every mathematics or computer science person, is to make it faster and better. So how do I solve this problem? So I just apply some common sense to try and solve this problem. So I just look at it and say, okay, my common sense will tell me that if I can find a path from the source to sink, then I can send some flow through that path. Can somebody tell me a path from source to sink? One person loudly. 1, 2, 4, 5. 1, 2, 4, 5. 1, 2, 3, 4, 5. 1, 3, 4, 5. So many paths are there. I can evaluate all paths and do it. Is it a good algorithm to evaluate all paths? No. So we don't follow. But let's do it one at a time. So what I will do is, since I don't know the network, I am looking at checking 1, 2, 3, 4, 5 is a path or not. 1, 2, 3, 4, 5 looks 1. So find a path from S to T, source to sink, and I can send flow on it. So the first one is I take 1, 2, 3, 4, 5 as a path. Don't ask me why I am taking 1, 2, 3, 4, 5. I am doing it for a reason. But we will start with 1, 2, 3, 4, 5. It's not a wrong, bad path. There's nothing like a bad path and a good path. Right? All paths lead to the destination. So if I take the path 1, 2, 3, 4, 5, 1, 2 can allow 20, 2, 3 can allow 30, 3, 4 can allow 35, 4, 5 can allow 25. So how much can I send? The minimum of the capacities is what I can send. Therefore, I can send 20 to update the flow. Update the flow and now create what is called a residual graph, update the flow. First I am updating the flow. 20, 20, this is 20, this is 20. The moment I do this, I understand that 1 to 2 is full. I can't send anything more in 1 to 2. I can actually leave this out. I can knock this out. Rather than put a 0, I can knock it out. This one, I had not sent any flow, therefore 40 remains. Here, I have a capacity of 30, I have sent 20, so 10 remains. To begin with, 10 remains. Similarly, 15 and 5, the red color is after updating, and particularly when there is already a flow in it, the balance is shown in the red color. So now what I do is I look at this residual graph and try to see if I can get another path from source to sink and try to send it. Obviously, I will not use 1 to 2 because I can't send anything from 1 to 2. So let's say I use 1, 3, 4, 5. So 40, 35 and 5 minimum is 5. And once I update it, I can create another residual graph and I can continue this. Are we okay? This is provided I have a way to see the graph in front of my eyes, and it's a small graph and I can do all this. Later how you write an algorithm will come later. So I can do this. So I continue, keep doing this. When I do this, I first start with 1, 2, 3, 4, 5. 1, 2 has reached the bound, I knock off 1, 2. Then I did 1, 3, 4, 5. I put a 5 there. And then I did a 1, 3, 5. I got another 20. So I have a flow of 45 here, and the residual graph will look like this. So after 3 iterations, after 3 paths, this is how my residual graph will look like. Now can I send any flow? Is there a path? No. So my algorithm will terminate by saying the total flow is 45. But what was the total flow? 55. So something we have missed. Right? Yes. Quick couple of things. With every, now this is a very basic thing called flow augmenting path algorithm. I find a path which can augment the flow. When I say augment the flow, increase the flow by a strict positive quantity. So flow augmenting path algorithm. And every time I find a path and decide this 20, one of these arcs is filled to capacity. Because I am taking minimum of the possible flows, one of the arcs is going to capacity. Right? in some ways, if I have 8 arcs, in 8 iterations I can finish. In a maximum of 8 iterations I can finish. Because every iteration is one path, and every path knocks off one arc. So at the end of it, after m iterations, this will go. Fine? Fine. At the moment. Now let us do something else. Let us do the flow augmenting path algorithm slightly different. First time I chose the paths in a certain order. Now that's why I started with 1, 2, 3, 4, 5. Now I am going to choose the paths in a different order. Now this is the order. So first I do 1, 2, 5. 1, 2, 5. So flow is 10. 2, 5 has reached the bound. If I am going fast, tell me, it's very simple. So I am going slightly faster than normal, unlike Simplex, which might have been new to a few people. This is simple addition, subtraction, so it's okay. If you want me to go even slower, I can do it. This speed is enough? Right. So now I do 1, 3, 5. I add another 20. 1, 2, 4, 5. I add a 10. 1, 3, 4, 5. I add a 15. Now this is how my residual graph looks like after I update. Now can I augment? Can I find a path? No? But now I have got the 55 that you know. Right? So there is something about the choice of the path which terminated with the incorrect answer, and some other choice gave me the correct answer. So I should do either two things. Either I should get my choices correct, or I should have a way to get that 55 from that 40. Both have to be done. At least one of them has to be done. We will do the other one. How do I get that extra 10? Where is it hidden? And how do I get that extra 10? We will see first. Then we will see what is the basis of this choice that has actually helped us do it. How do I get the remaining 10 units? Okay, how do I get the remaining 10 units? How do I know that there are no more flow augmenting paths? So go back to this. Now at the moment, this flow is 45. This flow is not 55. See, 20 plus 25. This flow is 45. Okay? That's the old solution, the 45 solution. This is your residue for that 45, with the only difference that I have introduced this 20. The old residue did not have this 20, and therefore you said there is no path. If you want, I'll show you the old one. See, this is the old residue. So now what I have done is, I have changed this, and I have put this 10. I put this 10. Okay, I put this 10. What have I done? I'm sorry, I put this 20. 10 is anyway available in this direction. 20 is flowing here. I'm just putting this 20 in the opposite direction, just to illustrate something. You can ask me another question, why have I not put this 25 in the opposite direction? You can ask me why I have not put another 20 in the opposite direction, but right now I have not done that. I'll explain all of that. Right now I am just adding this 20 in the opposite direction. And the moment I add that 20 in the opposite direction, can you find a flow augmenting path in this? Which is a flow augmenting path? 1, 3, 2, 5 is a flow augmenting path which can augment the flow by 10. So this is the way to correct the first one. Which means I have to start defining the residual graph slightly different. Till now, my definition of the residual graph was this. Till now, the definition of the residual graph was only this. Which means the capacity is 40, flow is 25. I can send another 15, so I put a 15. Capacity is 20, I can't send anything, knock off. Now what I have done, the residual graph now has, I did all the old ones, and I have added a 10. Strictly speaking, I should have added a 20 here, and I should have added a 25 here. You don't want any flow to come back to the source, and you don't want any flow to leave the sink. Therefore, those arcs that are attached to the source and sink will not have opposite flows. Only the arcs that connect the intermediate nodes can have opposite flow. So ideally, I should have put this 25 here, and I should have put the 20 here. Okay. Now what I have done, there is a flow of, now we have put only this, and let me explain. There is a flow of 20 from 2 to 3 and no flow from 2 to 5. So what can I do? I divert 10 units from 2 to 3 to 2 to 5. I divert 10 units from 2 to 3 to 2 to 5. Okay? Therefore, out of this 20, only 10 units are flowing here. Now I have to top up this 10. So I have capacity 10. So I send a 10 here. So this is taken care, that is taken. I am able to increase by 10. Repeat. By adding this 20 that goes here, now 20 units of flow is happening here. Now I am diverting 10 units to this and sending only 10 here. So this is having 10 less. So this 10 is augmented by this 10. And this 10 which is extra has come here, finally reaches through that 10. So the total flow has increased by 10. Okay? This is the trickiest part to understand in this algorithm. And once you conquer that, look at this word. Once you conquer that, it becomes so easy. Right? Right. And you always have to remember that I am diverting the flow. You take away flow, but you should not think of it as I am taking away. How can I take away 10? 20 has become 10, and yet increase it by 10 is always a question that will haunt you. So you have to remember this taking away is essentially diverting. So this 20 that is coming here is now diverted as 10 plus 10. So the 10 extra is reaching the destination. How can that 10 reach the destination unless 10 has to come from source? So put a 10 here and augment it. So you get this. Right? So I increase 1,3 by 10 units to get flow equal to 35. So that flow is conserved in node 3 and the net flow increases by 10. So create a flow augmenting path 1, 3, 2, 5 with minimum on. Right. Now how does the flow augmenting path algorithm work? We will see that. So now what I do, this is my original 45, this is the plus 10 which is 55, so now I have got my total flow 55. Now how does the thing look like? This is how this is for 45. So first I did all the residues, then I add arc. If there is a flow ij, where ij do not belong to source or sink, then the flow arrow is reversed. So now there is a flow of, one second. This is afterwards. This is after I put that. This is after 10, 55. Okay, I have augmented 55. After that, I am drawing the residual network. Okay, I am drawing the residual network after that. how does the residual network look like? Now here 2020 no arc, 40 35 5, 30 10 20 20, 35 25 10, 25 25 0 knocked off, 20 20 knocked off, 10 10 knocked off. And then I look at the flows. Flow Ij don't belong to source or sink, reverse it. So Ij don't belong to source or sink, there is a flow of 10 here, put the opposite 10 here. There is a flow of 25 here, put the opposite 25 here. That's all. Because there is a 25, but J belongs to sink, so I don't do that. 2020, I belongs to source, I don't do that. So this is my residual network. Now see whether I can get a flow augmenting path. Can't, because phi is cut off. So I can't do that. So the algorithm stops. Now how does this algorithm work? Flow augmenting path algorithm draws a residual graph. Residual graph R capacity is Uij minus Xij greater than 0 if there is remaining capacity. Arc Ji has value Xij greater than 0, no negative arcs from S and T, no flow arcs in the opposite direction from S and T. Find a flow augmenting path, use the residual network and find the maximum flow possible. Add this minimum value to Xij if it is a forward arc and reduce it if it is a backward arc. Therefore, when I did this, if you see carefully, when I did 1, 3, 2, 5 and increased to 10, this will be 10, this will be minus. So this or the other way, I'm sorry. Yeah, this is the one. If you see here, finally, 20 was the original flow. This is the direction, plus 10, minus 10, plus 10. So 20 becomes 10. Right? So when you take a backward arc, when you are diverting the flow, you subtract. So this is how your flow augmenting path algorithm works. At minimum if it is a forward arc and reduce it if it is a backward arc. So backward arc essentially diverts the flow. So this is your very basic flow augmenting path algorithm attributed to Ford and Fulkerson, 1957. Any questions? Fine? Sure. Now we are going to see slightly more advanced concepts, therefore I am asking. You're okay? Right. Now let us do this. Then you have these simple questions. 1. How many flow augmenting paths can I and should I get? Number 1. Number 2. This backward arc looks interesting but a little confusing. Can I have an algorithm that does not have this backward arc and all that? Can I do this with minimum number of flow augmenting paths? And how do I know that no more flow augmenting paths exist? How do I write a program or an algorithm to detect a flow augmenting path? Here this graph is, I can see the graph, so I know path and all that. But how do I write an algorithm which will do it? All these questions have to be looked at. We'll look at it, each one of them. So implementation of the flow augmenting path is this. Mark S as labeled and unscanned and the mark rest of them as unlabeled. This is the source, labeled and unscanned. If all labeled nodes are scanned, stop, else choose a labeled unscanned node, scan I. I am not very comfortable with the CS way of doing things, but nevertheless this is the algorithm. Okay, this is self-explanatory. So this is how you do the algorithmic portion of implementing a flow augmenting process. Okay, right. But I'll do it the way that's more comfortable for me rather than go through this lovely iterative procedure that is outlined. So let's do a labeling algorithm for the same problem. Okay, we'll do the labeling algorithm for the same problem. So there are 5 nodes. I label them as L1 to L5. So the simplest labeling algorithm is start L1 is the source. So put a plus and it has infinite capacity. So now start with node 1 and see whether there is a forward arc with leftover capacity. So 2 is available, arc 1, 2 has a capacity of 20. So label 2, put L2 as plus 1 and 20. Plus 1 because it comes from 1. 20 is the minimum of this 20 and an infinity that is available here, so 20. So node 2 gets a label of plus 120. Now take 2 and see whether I can move forward if there is a forward arc, 2 to 3. So L3 is plus 2 and 20 because node 2's label is 20. This is 30. Minimum of 20 and 30 is 20. So label 3, node 3 also has a label of plus 2 and 20. Remember, it's not 30, it's plus 2 and 20. It's like saying I am sending 20, 20 is here. So what I can send here is the minimum of the available 20 and the capacity 30. So it is 20. So from 3 you check again. I can go to 4, I can go to 5. So I do 1, 2, 3, 4, 5 with 20 and I update the flow. Okay, I can update the flow. Now L1 is plus infinity. 1 to 2 I cannot go because it is full. So I go from 1 to 3. Okay? But remember, I create my residual network and do it. So when I create a residual network, this 20 that is flowing here would give me a 10 residue in this direction and give me a 20 in the other direction. Correct? It will give me a 20 in the other direction if I draw the residual network. Therefore, from 3 I can go to 2. Therefore, I will put L2 as minus 3 and 20. Minus 3 indicates a negative arc. It's based on flow. So the moment I go here, the flow is 20. Flow is 20. Here it's 40. So L2 becomes 20. Now I can go from 2 to 4. So from 4 I go plus 2, 20. L5 is plus 4 and 5. Therefore I update 5. Total flow is 25, but I have to update it. When I update this, this 20 has become 15. It's reduced. Right? Negative arc has come in. Now go back, L1 is plus infinity. There is still capacity here. This is used completely. There is still capacity here, L3. Now L2 is minus 3, 15. L5 is plus 2, 10. I can actually do 4 and 4 to 5, but I come to 4 and then 4 to 5, I realize this is knocked off. So from 4 I cannot do much. I go back to 2 and I implement 5. So 2 to 5, I get total flow is equal to 10. Finally, you will realize whatever comes as L5 is the flow. See, 5, 10, flow becomes 35. Again repeat the algorithm. I will now do L1, L3, again L2, L4, again L3 and L5, flow is equal to 5. I do some 1, 3, I do 1, 3, 2, 4, 3, 5. I do something like that, a tricky kind of a thing it does, and then it does the other one, and finally gives you an algorithm. gives you that technique. Okay. So this is the kind of rudimentary algorithm which is done. This can be implemented slightly better. I have not shown the implementation that well, but this is how this algorithm is implemented. I've missed out a small portion. I've missed out the C, which is the set into which the scanned nodes are coming and all that. So you'll do scanned, unscanned. We're actually doing all that. The only difference is this thing will be avoided if I am doing that. I think this step will be avoided if I do that C correctly. But essentially this is how the algorithm works to get you. So that's how you implement it on a computer program, but this is the most rudimentary and basic algorithm that is done. Now can we make it faster is the next one. What else do we do? What are the algorithms? So we will see 4 algorithms today. One is the flow augmenting path algorithm, which we have seen. There are slightly better versions of it. Then we will see capacity scaling algorithm. We will see shortest augmenting path algorithm. And we will see pre-flow push algorithm. So these 4 algorithms we will see. All 4 we will see with the same example. So this 55 will keep coming as a magic number till I finish. First I will look at these 3, and in between I will talk about computational aspects. Otherwise in the end I will talk about computational aspects. We have already seen the basic version of the flow augmenting path algorithm. We will see a slightly more advanced version as well at some point. So first is you do what is called capacity scaling algorithm. First is one of the standard complaints against the traditional flow augmenting path algorithm and the labeling algorithm the way we have done is often given by this example. You look at any book, what is the maximum flow possible? 2000. How many flow augmenting paths are possible? 2. If I can see this figure, I will say take 1, 2, 4, 10,000, take 1, 3, 4, 10,000 over. Correct? But if I put it in a computer program, I will first do 1, 2, 3, 4, which will give 1, and then my labeling algorithm will now do, it will do 1, 3, 2, 4, which will give this 1. It will take away this 1 and divert and add 1 here. Then it will do 1, 2, 3, 4, 1, 1, 3, 2, 4, 1. It will do it about 2000 times and finally terminate. Right? That's often the difficulty. This difficulty can be overcome. At the same time, the message is, if I simply start by saying, I will start with a network like this, to begin with, I will not consider all the arcs. I will consider only a subset of the arcs, such that each arc is above a certain capacity. And then progressively minimize that capacity and go. And I said, now initially I don't take this fellow. I'll do 1,000 over. After that, I will have a network which is like this. And the algorithm will terminate in 2 steps. Correct? The moment I put 1,000, the residues are all 0 here, 0, 0, 0, 0. All of them are either attached to source or sink, so I will not have the backward arc coming. So this is my residual network, and the algorithm stops in 2 iterations. So typically a capacity scaling algorithm starts with a slightly higher capacity and then does it. Suppose I say 25 is my limit in this network. Now don't worry about this network. we are not going to use this. So suppose I say 25 is the limit. So this is how my network looks like. This is not residue, this is the original network. I have just knocked off all arcs that have less than 25 to begin with. How do I choose that 25 is a different question. But if I have chosen 25 as the initial capacity, this is how my thing looks like. Now what is your flow augmenting path? 1, 3, 4, 5. There is only one flow augmenting path. 1, 3, 4, 5 with a capacity of 25. Right now no more path exists, 25. Now use flow greater than or equal to 15. Reduce that capacity. Now use it 15 and now go back and start doing, this is all updated, 15, 10, this is knocked off. So all that updated. So I will have 20 as my flow. I use the path 1, 2, 3, 5, 1, 2, 3, 5, right? For example, after I take this path, now I am putting flow 15. There is an arc with 10 which I am not using because I am using flow greater than 15. Here the residue is 15, so 15 comes. So this becomes 1, 2, 3, 5 with another 20 as your flow. No more path after you update. Now go back and do flow equal to 10. I'm sorry, this is a mistake. So use flow equal to 10. And once you use flow equal to 10, this is how your residual network will look like. Okay, your residual network will look like. So your minimum will be 10 and hold on. Yeah. So this is how it will look like. This is your residue. And then you will do a 20 was flowing here this way. 3, 4 will have a 25 flowing here in your residue. So that will be a 25 that's flowing here this way. Okay. So 20 is your flow. Okay. Then you use 10. You will have this and then. Shall we do it again? I think I haven't done it extremely well. Just quickly do it again. So, this is where you are. So use flow greater than 15. There is no path. So let me just do that because I don't want to do it in a hurry. First you do 25. So what you do is your path is 1, 3, 4, 5 with 25. That's the path you have taken. So 1, 2, 3, 4, 5. So 1, 3, 4, 5 is the thing. So there is a 15 which is here. This is your residue. So this is knocked off. This is residue is 10. I have a 30 here. I have a 30 here. That's all I have. All right. After I take that 1, 3, 4, 5 path, so this becomes 15, this becomes 10, this becomes 0, so no more path. Now I am using 15 at this point, so I am adding a 20 here. I am not adding this 10 here, I am adding this 20 here. This is what I have. And my residue will show a 25 here because the earlier flow was 25. So my residual network will show a 25 flow here. Are we doing okay? This 25 won't get reflected. This won't get reflected because it goes to sink. This is from source. This is the only way. Now find a path. I can find a path. This is my next network. So I can find a path 1, 2, 3, 5 with value equal to 20. Okay, 1, 2, 3, 5 with value equal to 20. So this goes off. This is 20. This also goes up. 1, 2, 3, 5 with value equal to 20. Now this 20 will get reflected as 20 here. Now I don't find a path because all this is knocked off. So now I keep the minimum as 10. I go back and add this 10. Okay. So now I can get a path which is 1, 3, 2, 5, which is 10. I get a path 1, 3, 2, 5, which is 10. 1, 3, 2, 5, which is 10. So 25 plus 20 plus 10 gives me my 55 in exactly 3 paths. Fine. The first version had 5 paths. Second version took 4 paths. This takes 3 paths. But some more computation is required. Are we doing fine? Any questions? How I am choosing, that's the next question. But as regards algorithm, you are okay? There are some thumb rules and guidelines. Choose the maximum of these and then choose divided by 2 and you can do that. Or you can do 2 to the power n is equal to u, where u is the maximum, and you can do that. And then you, at every stage, divide it by 2 and take the best integer. So there are these typical search ways of doing it. So you can do that. So this is the essence of the capacity scaling algorithm. The algorithm remains the same. Draw the residual network, find a flow augmenting path, update the flow. The only difference in this algorithm is in the earlier one, you took the entire graph network all the time. Now you will not take the entire network. You will take part of the network and keep adding it as the capacity reduces or get added, and you do it. So this is called capacity scaling algorithm. So we have seen the basic flow augmenting path algorithm and the capacity scaling algorithm. Both of them work with the residual network and then find the flow augmenting path in the network and then update the flow augmenting path. The next one is called the shortest augmenting path algorithm. And what do I do with the shortest augmenting path? Now before I augment, or how do I find the path? If you see carefully here, before we put the negative arc, when we stopped at 45, you observe that I had carefully taken 1, 2, 3, 4, 5, 1, 3, 4, 5. These were all longer paths. Whereas the second version, when I did this, you see, I have taken 1, 2, 5, 1, 3, 5, 1, 2, 4, 5. So I moved in shortest path. So shortest path seems to help. So how do I find the shortest augmenting path? I do it this way. Put a label 1 for the sink. As usual, take the residual graph. Put a label 1 for the sink. Now this will take a label 2 because one arc directly connects this. This will take label 2 because one arc connects this. This will take label 2 because one arc connects this. Now this will not be relabeled because there is a connection, so it will stay at 2. And once this stays at 2, this will become 3, this also gives 3. So once the index is 3, I know that I have a shortest path with 2 edges that connect source and sink. Please remember that this is not updated, node extras kind of thing, right? So this is not updated to 3. It will stay at 2 because it's the smaller of n plus 1 and the existing label. The existing label is 2. From the connectivity, I will get plus 1, 3, but I will use the smaller of the two. So it will stay at 2. So now I know I can have a shortest path of length 2 with 2 arcs. So I choose 1, 2, 5 to begin. So once I choose 1, 2, 5, I go back to the residual network, and if I go to the residual network, my flow will be 10. Then I update the flow and create a residual network. Now with that residual network, once again I run the shortest. See? I run, then I get 1, 3, 5. Like this I can do the shortest path algorithm, 1, 2, 4, 5, create residues, update flow. Now you see the shortest, this index has become 4, therefore I have to do this. I have to do this. 1, 3, 4, 5. So I will have a path of length 3, and I do that. I run the shortest augmenting. No path, flow is equal. So we have seen 3 versions. The flow augmenting path algorithm, capacity scaling algorithm, shortest augmenting path algorithm. All the 3 basically try to find an augmenting path. Do it slightly differently. Flow augmenting path was more rudimentary. Capacity scaling took a reduced network, found out flow augmenting paths and updated, created residues and did it. Shortest augmenting path did not take part of the network, took the entire network, but found the shortest path at each stage and then did it. So obviously, if I am a little more intelligent, what do? I apply the shortest path, augmenting path on the capacity scaling algorithm and do it. So I can gain. If I can gain, I gain. Both are possible. People did it. Unfortunately, people are much smarter and older than us. So they did those things very quickly. That is why you read about all these Ford, Fulkerson, Edmonds, Karp, all this, you keep reading about all these people. Right? Okay. And more recently, Ahuja, Tarzan, all these names. Fine? Goldberg. So these kind of names. So somebody did it. So you can do the shortest augmenting into the flow augmenting, and you can do it. So all the 3 do it. Now we'll start looking at how these algorithms evolved over a period of time and how they became faster and faster, who did what. Now we will define something called coherent blocking flows in the shortest augmenting path algorithm. One thing that all the 3 did was, given a network or given a residual network, it will identify one path and then it will go back and update. It will create another residue and then take one path, update, take another. The next algorithm is, I have a residue, I work with that residue as much as I can, then I go back, I update the residue, and then I work with that residue as much as I can and do it. Now what also happened was, the Ford Fulkerson's original algorithm came in 1957 or whatever. Edmonds and Karp came somewhere in 71, 72. We'll see what Edmonds and Karp algorithm did at some point. There is also something called Dinnick's algorithm, which came somewhere in 70. Now Dinnick's algorithm is an intelligent way of doing the flow augmenting path algorithm, with the additional thing that with one residue, I don't identify one path and update the residue. I take the residue, update as much as I can, go back, create another residue and do it. He said that's slightly faster than the other one. How does he do that? So he creates this. How to find out core and blocking flow. Now essentially you apply the shortest augmenting idea on this. So first this is my given network. Label the source as 1. Relabel the rest of them with smallest possible label such that the label gets a +1 if I can augment flow. For example, 1 to 2, so 2 gets a label of 2. 1 and 3, 3 gets a label of 2. But you see there is an arc between 2 and 3. So if I apply this, then this fellow should get 3. So I don't update it to 3, I keep it as 2. At the end I make sure that if there is an arc ij that can augment the flow, the label dj is equal to di plus 1. Rest of these arcs I remove them to begin with. That's the reason why this fellow is not here. That's the reason why this fellow is not here. Now this is called the core or the residual network. Now take this residual network and apply the flow augmenting path algorithm intelligently. So when you apply the flow augmenting path intelligently on it, you will now send 10 across this and 20 across this. Remember, you will do the shortest augmenting on this. You are not doing the normal flow augmenting, you are doing the shortest augmenting. Shortest augmenting is obvious because 1, 2, 3, 1, 2, 3. This is not going to help. So here if I do something, nothing will happen. So I run the shortest augmenting path and I quickly send a 30 with the same residue. Now once I have sent the 30, I go back and redo the whole thing. So this is my given graph. This is my given graph. Right? This is my given graph. Now look at my core. Relabel the node such that dj is equal to di plus 1 and put those ij r. Obviously, this is fully used, so this is knocked off. So redefine the core. This has spare capacity. This is fully used, so knock it off. This is my existing one, so there is no residual, doesn't have the other flow and all that. So this is my new core after one iteration. Then I quickly run the algorithm. Now this is 4, so I have to do 1, 2, 3, 1, 2, 4, 5 and 1, 3, 4, 5 and I do a 10 plus 15, 25, 30 plus 25, 55. No negative arc, no backward arc, nothing. Right? This is called Dinnick's algorithm. This algorithm is a more intelligent way of using your flow augmenting path algorithm and ideas from shortest augmenting path algorithm. But the fundamental difference is, given a residue or a core, you try to find the blocking or limiting flow and then create a core and then find the blocking. So this is called Dinnick's algorithm. Then we will do what is called a push algorithm. This is the last. Then I will do the computational aspects of it. So what have we seen? Ford and Fulkerson's flow augmenting path algorithm. The idea of the negative flow to make the Ford-Fulkerson algorithm as optimum. Then a labeling version of the Ford-Fulkerson algorithm. Then shortest capacity scaling algorithm. then shortest augmenting path algorithm, and then the Dinix algorithm, which is an intelligent implementation of everything. Now look at this algorithm, which is possibly the last one for the day, push algorithm. I am right now going to call it push algorithm. I am not going to call it free flow push and all that. There are several versions of free flow push. So we will call it a push algorithm. Basically, the push algorithm pushes as much as it can. Now, how does the push algorithm work? So the source has infinite capacity. So what does the source do? The source is sending 20 here, and it is sending 40 here. So source pushes 20 to node 2 and 40 to node 3. I am just doing it a very common sense way. So what is 2 doing? 2 will try to push as much as it gets somewhere. So 2 pushes 30 to node 3. So node 3 now has, pushes 20 to node 3 because it gets only 20. So it pushes 20 to node 3. So node 3 has 60. So 60, it pushes 35 here, it pushes 20 here, it has to send back the 5. You have to assume that intermediate nodes do not have a way to store. So it sends back either to 1 or somewhere. So this here it's pushing 35, so this 20 goes straight. Now this fellow gets 35, now he sends 25 and he has to send this 10 back, so he sends this 10 back. And once he sends this 10 back, this guy has to send it back. He doesn't want to send it to the source, he sees if he can send it somewhere else, he is sending it here. And once he is sending this here, this fellow pushes back to 5, so you get your 50. That's my common sense way of using a push algorithm. But then I have to intelligently code it as a different issue. It should not go to a loop. All these things I have to ensure. So what do? This is what happens. So if I kind of write what I have told you, the different steps will be infinity 0, 0, 0, 0. Now this is sending infinity 20, 40, 0, 0. Now this 20 is coming back here, so infinity 0, 60, 0, 0. Now the 60 is becoming 35 and 20. So more intelligently it will become 25, 35 because this can send, actually it should be 35. So first it is sending 35, so it is keeping 25. Then it is sending a 20 here and keeping the 5. Now this is sending 25, so this becomes 45, these are extra. And then the extra ones have to come back. So 15 is coming back to 3. Now 15 is going to 4. Now it can't go to 5, so it comes back to 2 from 4. Then 10 goes here, becomes 55, and the 5 comes back to 4. Some intelligent way of doing all this I have to do, and I have to code it well. How do I code it? Somewhere, it doesn't exactly map what I told you. Somewhere you are throwing a ball back and that fellow throws it back. Finally, it comes back to the source. The ball is a barrel containing 5 units of flow. It's very obvious because this is 25, 45, 55, this is 60, so 5 has to come back. It's like playing that nice game, no? You keep throwing and you have to catch and throw to somebody. Like that, it keeps throwing around. Now, one way to understand this algorithm is, very important way to understand this algorithm is this. You have to assume that these 5 nodes are like water tanks from where water is going to flow by gravity. No pump. So when will water flow by gravity? When the height of one is more than the height of the other. And how else will it flow? It always flows where the height difference is maximum. that is where it flows first by gravity. Correct? Pressure head and all that. The only thing is, we intelligently have a way by which these tanks can be kept at varying heights, and as a decision maker, you will have a way to suddenly increase the height of a tank. And when you increase the height of the tank, it can flow. That's the only thing you will do intelligently. After that, it takes care of itself. Fine? Therefore, you associate something called the height of a node, and you associate the amount of flow that is sitting in that node. And remember, intermediate nodes do not have a way to have flows sitting there. So any flow that is sitting in an intermediate node is called an excess flow. It cannot sit there. There is no place to sit. The ball has to be thrown back. It's a hot ball, so you have to throw it back. But it's called excess flow. So at the end of it, all excess flow has to leave, and excess flows finally will go to the sink or come back to the source. So excess flows have to be sent. So every node will have two labels. One is called the height, and the other is called the excess flow that is present in that node. With this background, we will start the algorithm. How do we bring this to a structured algorithm? So first is, height is, put this as maximum height. There are 5 nodes, so put this height equal to 5. This fellow has initially infinite capacity. Correct? So put this height is equal to 5, which is the number of nodes in the network. Now the moment the height is 5, all these heights are 0. 1 and 2 is connected, 1 and 3 is connected. Automatically 20 and 40 will flow from 1 to 2 and 3. Right? Both of them have height 0, therefore at the same time 20 and 40 will flow. Now excess flow is infinity 0, 0, 0, 0 to begin with. Now on, say game starts, and then push 20 from 1 to 2 and 40 through 1 to 3. Now the moment you do that, the x12 becomes 20, 20, 40, 40. Height remains as 5, 0, 0, 0, 0. The excess flow is infinity 20, 40, 0, 0. Excess flow is like a hot ball which has to be thrown. So choose that node which has maximum excess flow. Other than source and sink. Source and sink you can store as much as you can. So you will choose node 3 which has 40. This 40 has to go. Right? 40 has to go. Now look at 3, and from 3 I can send to 3 to 4 and 3 to 5. Okay? I can send 3 to 4 and 3 to 5. But 4 and 5 have height 0, 0. So it cannot flow. So what do you do? Increase the height of 3 by 1. Right? So 3 becomes 5, 0, 1, 0, 0. Now the moment height of 3 becomes 1, it can flow from 3 to 4 and 3 to 5. It can flow in slightly different ways, but push a little intelligently. 3 to 4 is maximum. Push 35 to 3 to 4 and push the remaining 5 from 3 to 5. So now this 3 is happy. All this hot ball has been thrown. Now there are excess flows here. Now choose that one which has the maximum excess flow. So choose this 4. 4 is struggling what to do with this 35. So now what happens is, excess flows have become 35 here. So from 4 it has to go. So from 4 it can go to 5. But 4's height is 0 and 5's height is 0. So increase 4's height by 1 So 5, 0, 1, 1, 0. So 4 to 5 can absorb 25. So quickly send 25, push 25 to 5. Push 25. So you get 5, 0, 1, 1, 0. 25 goes in the excess flow, 10 is remaining. Now this 10 in the same iteration I have to send it. The moment I choose the node, everything has to go from that node. Okay, everything has to go from that node. So 10 is remaining. So this 10 cannot go to 5. So this 10 has to be pushed back. So when 10 is going to be pushed back, push 10 units back to 3. How do I do that? Right now the height of 4 is 1 and the height of 3 is 1. So make height of 4 2 so that 10 units are pushed back to 3 and nothing can go to 5 because this guy can't take any more. So infinity 20, 10, 0, 30, that's the excess flow and those are the heights. Now 2 and 3 have excess flow, 2 is boiling with excess flow of 20, take 2. So this 2 has to go. Now what are the heights? 2 and 3, 2 and 4, 2 and 5. Right now these are higher, 2 and 5 can flow, 10 can flow. So just increase 2 sufficiently to send 10 units to 5. I hope that's what we are doing next. Push 10, 2 to 5. So make this 1 and push 10. Okay, push 10. So now I'm still grappling with another 10 here. I'm grappling with another 10 here. So 5, 1, 1, 2, 0. So I have to push to 3. So I push to 3. So I increase the height by 1 more and push 10 to 3. Now 3 is the fellow grappling with 20. Now when 3 is the fellow grappling with 20, now it can push 15 to 3, 5. Can push 15 to 3, 5 because this height is 1 and this height is 0. So it can push 15 to 3, 5. And it still has remaining 5. If this has capacity, so it will increase its height by 1 and push 5 to 3, 4. So this is where you are. You have reached the 55 flow, but the algorithm has not stopped because 5 is sitting at 4 and hot. So 5 has to be pushed. It cannot be pushed forward, it has to be pushed back. So it is pushed to node 3 with 4 increasing its height 1, 2. So height is 2, 3 has a height 1, so it pushes back to 3. Now this game kind of continues, but this with the height increasing every time for a couple of iterations, the way this happens. So it keeps repeating, and then at the end what will happen is, it will move between 3 and 4 till somewhere the height exceeds 5. And the moment height exceeds 5, 1 is at 5, so it will automatically be pushed back to 1. And finally the algorithm will terminate with max flow equal to 55. This is called push algorithm to begin with. It has several versions, free flow, push, many other versions that are existing. But this is the principle. Obviously you don't want this triangle game to happen, so you'll have intelligent ways of pushing it back and all that. This is a more recent algorithm. Before we wind up, maybe I'll take another 10 minutes to wind up. Now we have to understand what is a flow and what is a cut. There are two definitions of cut. The standard definition of cut is forming the nodes into two sets such that the source is in S1, sink is in S2, and the rest of them are either in S1 or in S2. That is the most accepted definition of a cut. There is a slightly different definition which Rottel's book uses. It says just make sure that source is in S1, don't worry about the sink. But we will follow the first one. Source is in S1, sink is in S2, and the rest of them are in the other. For example, if I take this network and draw this red line and tear it into two, then I realize my S1 is 1 and 2, S2 is 3, 4 and 5. Node set. Alright? And then I am tearing this network into two, which means I am breaking this, and if the rest of these arcs have infinite capacity, or already there is infinite capacity here, I can always send 40 plus 30 plus 30 plus 10 through this. I think that if you know data structures and how to represent arcs, okay, then you will understand. First part is a little tricky. You have to define head of an arc, tail of an arc, and you have to do that. If you have learnt it, so be it. If not, learn it. So if you do that efficient representation, then you can show that each augmentation is order of complexity of m, where m is the number of arcs in the network. The computational effort in each augmenting path is order of complexity of m, order of the number of arcs in the network. This is a very basic thing. If U is the maximum capacity, and for the sake of theory, all the arcs are all but one have, you remember this, the other one that I drew here, 1000, 1000, 1000, 1000, 1. Somewhere the flow augmenting path will require 1000 iterations in the worst case. If that was 1 crore, 1 crore, 1 crore, 1 crore, 1, then it would involve 1 crore iterations. So the worst case, it will do n into u, where n is the number of nodes actually, into u. U is the value that you have. So it will finally do m into n into u. Nu augmentations are possible finally with each node, and therefore you will get order of m into n into u. This is the old algorithm where you can have this. Capacity scaling will help there. Now this is not polynomial because if u is the maximum capacity and can represent 2 to the power something. So it's not polynomial in this. So the first basic implementation is not a polynomially bounded algorithm, the first algorithm that we saw. Then Edmonds and Karp showed that the first labeled, first scanned version uses no more than mn by 2 iterations, and therefore the order of m square n, because mn by 2 into order of n will give you m square n complexity. First scanned, first labeled was that labeling algorithm that I gave. Not only the algorithm, but the version that I wrote, that algorithmic text that I wrote is the first labeled, first scanned algorithm. That gives you m square n. Generally in a network, n is the number of arcs and m is the number of nodes. So you will have m square n that comes in. Then you look at Denick's algorithm. They compute a blocking flow in each iteration in order of mn steps. They also showed that it does not require more than n iterations. So it is m square n complexity. The earlier one is also m square n complexity. So Denick's is also m square n complexity. Perhaps the interesting contribution was how to do the blocking flow faster. So Denick's algorithm does the blocking flow in m square n, and Kumar and Maheshwari, Malhotra, Kumar and Maheshwari is another famous algorithm, one of the few places where you find a full set of Indian names coming. So what they did was they made that part faster. So the mn steps was made m square steps. Generally n is the number of nodes and m is the number of arcs. So you expect m to be bigger than m. So order of n square, so their algorithm runs in order of n cube. So that's their contribution. Capacity scaling algorithm starts with delta is equal to 2 to the power log u, which is where that answers the question, how do I start that first value delta? and halves it till delta is equal to 1. So it solves the problem with m log u augmentation and runs in m square log u time. Again, when you have u non-polynomial because of this u thing coming in, and then if you put an efficient idea of shortest augmenting path, it does in mn log u, and then depending on u, it can be faster. And so generic free flow push runs in n square m, and there is a version called first in first out free flow push that runs in n cube. So this is roughly the computational angle to it. So different algorithms run with different complexities, and quite number of them are polynomial. So this is n cube is polynomial, m square n is polynomial. They are all polynomially bounded algorithms that make the problem run faster. So if you are solving large problems, you will not go to the Microsoft Excel solver and do it and run it by Simplex. You would rather do with, or alternately, if you have softwares which will solve the max flow problem, either commercially or otherwise, the max flow version, they will start using one of these algorithms. Several applications, of course, you can see this from many places. Most of this, I'll also give you my reference, but the only one which I added is the operator allocation problem, which we happen to work and try to look at it as a min cost flow problem. Every min cost flow problem can be solved as a max flow problem. So you have these applications. The rest of them are all taken from available material. Two excellent source of material which I have used. So please, Ahuja, McNanty and Orlin, very famous book on network flows. There are times you can even download a PDF version. The book is about 20 years old, so you can kind of download some chapters. 7th chapter, 6th and 7th chapter talk completely about this. Very good book, very standard book. Total's linear programming book is usually not available so much. So it's difficult to get. That book also has an excellent chapter on it. I think that's it. The end of the day. But any questions? Both are essentially kind of, you can call them as OR books, but both of them are written with a lot of CS flavor, the way the books are written. You actually start reading an OR book, you will know what is the flavor of the book. So both these books are written with completely computer science flavor, the way algorithms are presented. Is there a question? Please. Yeah.
So can the values be framed as linear combination of weights? For example, you include 3x1 plus 180x2 and 300x3 equal to 0. Can such values be framed as linear combination of weights?
Equal to 0? Yeah.
Or not equal to 0, so equal to some values. In case of face detection and face recognition problems, such kind of values place as a linear combination and more weightage is given to the eigenfaces.
I don't know the phase algorithm that you're talking, so I'm not able to comment. But they themselves are linear. That's the only thing I can say. So the objective function is a linear combination of the variables. I don't know the other algorithm. But whatever I've explained is the way to solve that problem. You may find better computer implementations, you may find more representations, but the fundamental algorithm is the way I describe the algorithm. Any other? Anybody else? Okay. Thank you.
Thank you so much, sir, for giving me a wonderful lecture. If you had CAC properly working, it would have helped everyone to sit here in a more comfortable way. I apologize for that, but now, after listening to him, you know why his NPTEL lectures are viewed as more than live views. So it is also available, And so please go and Google for those ethical lectures so you can, if some of the things you missed here, you catch it while watching those lectures. Thank you very much.